Hello everyone, you're welcome to this lesson. In this video, you are going to solve this question I have on the screen. The question says, four tugboats are used to bring an ocean liner to its pier. Each tugboat exerts a 5,000 pounds force in the direction shown. Determine A, the equivalent force couple system at the foremast O, and B, the point on the hull where a single, more powerful tugboat should push to produce the same effect as the original four tugboats. So let's look at how you are going to solve this question. Okay, so the first thing I'm going to do is to convert the unit of the force from pounds force to kilo pounds force. Okay, so let's look at that. So what you have to know is that 1,000 pounds force will be equal to 1 kilo pounds force. Okay, so in this case that we have 5,000 pounds force, that would be equal to 5 kilo pounds. So the unit of the force is going to be in kilo pounds and not pounds. Let's take note of that. And the first part of the question says that we should determine the equivalent force couple system at the foremast O. So what this means is that we have to find the total force acting at point O, and then find the total moment of the couple at what point O. So that's what you are going to do. So let's look at how you're going to do this. So you're going to start by calculating the resultant force, or the total force acting at what point O. To do this, you must find the components of what each of the forces acting on the ocean liner. So let's look at how you're going to do this. So each tugboat is exerting the 5 kilo pounds force on the ship. So we are going to resolve this force into components, but you see that they are all placed at a specific angle. So that means that their components are going to be different, so you have to find the components of all these forces, and after that you sum it together to find the components of what the resultant force. So let's start with the first force, which is acting at what point 1. So let's take this to be the surface of the liner. So we have the first force acting at this point. And then it makes an angle of 60 degrees with the horizontal. So you have 60 degrees here. So you have to find the component of this force. It will have a y component and then an x component. So let's look at that. So to find the component, we're going to take you first of all take cosine of the angle. Then that will be equal to the adjacent side over the hypotenuse. So let's name the first force as F1. And then that's equal to 5 kilo pounds. So let's look at that. So that will be equal to the adjacent side, which will be Fx1 over the hypotenuse, which will be 5. So we're going to have Fx1 will be equal to 5 multiplying cosine of what? 60 degrees. So let's see what you're going to get for that. 5 cosine of 60 degrees will give us a value of 2.5 kip. That's the s component for the first force. Let's look at the y component. That also be minus 5 multiplying sine of 60 degrees. Let's see what you're going to get. Minus 5 sine of 60 degrees. That will give us a value of minus 4.33 kip. So that's for the y component also. So we're going to do the same for the remaining forces too. So let's go ahead and then look at that. So let's take this to be the second force, which is F2. And then for that one, we've been given some dimensions. We have 3 here and then we have 4 here, which means that the hypotenuse will be 5. So we have a triangle like this. We have one side to be we have a triangle like this. We have one side to be 3, one side to be 4, and then here to be 5. Let's take this angle to be theta. This angle theta will be the same as the angle that the force will be making with the shape. So you're going to have the same angle theta here. Let's take note of that. So now let's take cosine of that angle theta there. Okay, so cosine of theta, okay, will be equal to the adjacent side over the hypotenuse, and then sine of theta will be equal to the opposite side over the hypotenuse. Okay, let's take note of that. Okay, so let's continue. So to find the component of the force, first of all, we're going to have to take cosine of that same angle theta. Okay, and then that will be equal to the opposite side. Sorry, that will be equal to the adjacent side, which is fx2, okay, divided by the hypotenuse, which will be what, f2, right? So you're going to have fx2, okay, to be equal to f2, which will be 5 multiplying cosine of what, theta, right? And then you're going to have fy2 also to be equal to minus 5 multiplying sine of what, theta, right? But we know that cosine of theta is equal to what, 3 on 5. So we are going to have fx2 to be equal to 5 multiplying 3 on 5. And then this and this will cancel out. So then we're going to have 3kip. And then for fy2 also, you're going to have minus 5 multiplying 4 on 5. Okay, and then they are going to cancel out. So at the end, you're going to have minus 4kip. So for the third force, okay, it is acting in the negative y-axis direction. So we're going to have our fy3 to be equal to minus 5kip. Okay, that's for the third force. Okay, let's take note of that. Okay, so let's do the same for the last force also. So for the last force, we have it to be acting in this direction, making an angle of what, 45 degrees with the ocean liner. Okay, so it will have components in this direction, the x component and then the y component. So let's take the cosine of that angle and see. Cosine of 45 degrees will be equal to the adjacent side, which will be fx4 over the hypotenuse, which will be 5. So you're going to have fx4, okay, to be equal to 5 multiplying cosine of what, 45 degrees. Let's see what you're going to get. 5 multiplying cosine of 45 will give us a value of 3.54 kip. Okay, that's for the x component, and then for the y component also, that's going to be the sine of the 45 degrees angle. That will be equal to fy4 over 5. That will be equal to, that will give us fy4 to be equal to 5 multiplying sine of what, 45. You notice that this is positive because it is pointing in the positive y-axis direction. Okay, so this will also give us 3.54 kip. Okay, so now to find the resultant force, you must just sum up the components, okay, of the forces. Okay, so let's look at that. So for the resultant force, you are going to have 2.5 I, okay, minus 4.33 J, okay, then plus, okay, plus the component of the second force, we're going to have 3I, okay, minus 4J, okay, and then for the third force, doesn't have an S component, so that will be 0, and then it has just a Y component, which is in the negative direction, so minus 5, okay, alright, and then for the last force, it has the S component to be 3.54, okay, and then the Y component to be 3.54 also. So now let's find the resultant of what this force is. Okay, so let's add the x component. You're going to have 2.5 plus 3 plus 0 plus 3.54. This will give us a value of 9.04 in the x-axis direction. And then let's look at the y component also. You have minus 4.33 minus 4 minus 5 plus 3.54. That also gives us a value of minus 9.79 G. Okay, so we've been able to find the component of the resultant force. So what you're going to do next is to find the couple moment about what the point of interest O. Okay, so when you find the couple moment about this point, then we are done finding the force and then the couple system. Okay, then we can the force and then the couple moment. Okay, then we can represent it on a free body diagram. Then we are done with our force couple system. Then we move on to the next question. So let's go ahead and then find the moment of what the couples. Okay guys, so now let's find the moment of the couples. Okay, so to find the moment of the couples, the moment. Okay guys, so now you're going to find the total couple moments about point O. Okay, so let's look at how you are going to do that. So the total couple moments, okay, about point O, the R there means resultant. Okay, this will be equal to the sum of the cross product of the position vector and then the force vector. Okay, let's take note of this. Okay, and then I'm going to equate this to, okay, I'm going to equate this to ax multiplying fy, okay, minus ay multiplying fx, okay, and then all this will be multiplying the vector k. Okay, that means like they will be in the k direction, okay, which is the z-axis direction. Okay, let me bring the sum here. Okay, so the sum of the cross product of the position vector and then the force vector will be equal to the sum of ax multiplying fy minus ay multiplying fx, okay, multiplying k, which is in the z-axis direction, where ax and then ay are the components of what the position vector. Okay, so the position vector r will be equal to axi, okay, plus ayg, okay, and then the force will have the following components: fxi, okay, plus fyg. Okay, so let's take note of this. So that's how can we have this. Okay, I'll explain this to you later. Okay, the reason why we have this formula here, okay, I'll explain to you at the end of the video. Okay, so let's look at that. Okay, so now let's look at how you're going to find the cross product. Okay, so to do that, you first of all have to find the position vector of each of the forces. Okay, so let's go ahead and then do that. So for F1, okay, its position vector, let's look at what you are going to get. For F1, you're going to move in this direction. Okay, its position vector from point O. Okay, you are going to move in this direction, which is minus 90 in the x-axis direction, and then in the y-axis direction, you move at 50 feet. Okay, so that will be plus 50, okay, in the y-axis direction. And then for F2 also, let's look at what you are going to have. So for F2 also, you move in this direction, that's in the positive x-axis direction, and then you move up, okay, at a distance of 70 feet in the y-axis direction. Okay, so for that one also, we are going to have 100i, okay, plus 70g. Okay, this is what you are going to have. So let's look at F3 also. So for F3, you're going to move at a distance of 400 feet in the y-axis direction, and then in the x-axis direction, and then the y-axis direction are going to move at a distance of what, 70 feet. Okay, and then for the last force also, let me clean what you have here. Okay, so for the last force also, we are going to move at a distance of 300 feet in the x-axis direction, and then at a distance of 70 feet, which is minus 70 feet in the y-axis direction. Okay, so for F4, okay, we are going to have 300 in the x-axis direction and then minus 70 in the y-axis direction. Okay, so these are the position vectors for the various forces. Okay, so you are going to find couple moments for each one of them. Okay, so let's look at that. So let's find a couple moments for the first force. Okay, for the first force. So we know the component of the force. Let me write the component here also. Okay, so for the force, you have the component, you have 2.5 I, and then minus 4.33 J. Okay, and then for this also we have 3I, okay, minus 4J, and then for this we have 0 for the I, okay, and then we have minus 5 for the J component. Okay, and then for this we have 3.54 for the I, and then 3.54 for the J. Okay, so let's compute for each one of them. So for the first force, we are going to have AX multiplying FY, right? So we know that the AX corresponds to the X component of the position vector, and then the FY corresponds to the Y component of what? The force vector. Okay, so we are going to have minus 90, okay, multiplying minus 4.33, okay, minus AY, which is 50, okay, multiplying FX, which is what? 2.5, right? So by K. So let's simplify this and see what you are going to get. So we are going to have minus 90 multiplying minus 4.33. Okay, that will give us a value of 389.7. Okay, and then this will be you will subtract 50 times 2.5 from that. So minus 100 and what? 25. Okay, so let's simplify this and see. So we are going to have 389.7 minus 125. That gives us a value of 264.7. Okay. Okay. Alright, so we are going to do same for the remaining forces too. So let's look at that. For F2 also, we are going to have 100, okay, multiplying minus 4, okay, minus 70 multiplying 3. Okay, so I'm going to simplify this at once. So let's look at what you're going to get. So you have 100 times minus 4, okay, minus 70 times 3. This will give us a value of minus 610k. Okay, let's take note of this. So let's do the same for the third one also. So for the third one, it has just a y component. Okay, so you're going to have 400, okay, multiplying minus 5. Okay, so let's see what you are going to get. So 400 times minus 5, that gives us minus 2000 k. Okay, let's not forget the k. So let's look at the last one also. So for the last one also, we are going to have 300 multiplying 3.54, okay, minus 70, okay, multiplying 3.54. Okay, so let's simplify this and see what you are going to get. So we have 300 multiplying 3.54, okay, minus 70 times 3.54. So this will give us a value of 1309.8k. Okay, this is what you are going to have. But you see that they are all in the k axis direction. Okay, so you can sum them up to get the total moment of the couples. Okay, so let's look at that. So you're going to sum everything up. Okay, so we're going to have the total moment of the couples to be equal to 264.7, okay, minus 610 minus 2000 plus 1309 0.8, okay, all multiplied by k. So let's see what you are going to get as our answer. Okay, so let's sum everything up and see what you are going to get. Okay, so we have 264.7 minus 610 minus 2000 plus 1309.8. So this will give us a value of minus 1035.5k. Okay, so this will be the resultant moment of what the couples. Okay, so let's take note of this. And also the unit will be kip feet. Okay, kip feet. Okay, let's take note of. Okay guys, so now you've been able to find the components of the resultant force and also calculate the moment of the couples. Okay, so this will be the free body diagram that you have to draw after doing that calculation. Okay, so we have the components of the forces here. We have the x component, and then we have the y component, and then this is the moment, the total moment of what the couples. Okay, and then this is the angle that the resultant force R will make with the x-axis. Okay, you can find this angle by taking the tan inverse of what the y component over the x component. Okay, so now let's continue. Okay guys, now let's look at the second part of the question, which says that we should determine the point on the hull where a single more powerful tugboat should push to produce the same effect as the original four tugboats. So let's look at how you're going to answer this question. Okay, so let's take this to be the ocean liner. Okay, let's take this to be the ocean liner, and then this time around we are using a single tugboat. Okay, so let this be the force that the single tugboat will exert on the ocean liner. Okay, then this force, okay, must be equal to the resultant of the forces exerted by the four tugboats. Okay, that's one thing you have to know. The force that the single tugboat will exert on the ocean liner must be the same as the some of the forces that the four tugboats exerted on it. Okay, and then for that value we got 9.04 I, and then minus 9.79 J. Okay, and then the unit was KIP. Alright, and then let's take this to be our point O. Okay, so we want the effect that the force, okay, exerted by the single tugboat will have on the hull to be the same as the effect that the four tugboats had on the ocean liner. Okay, we want the single force to have the same effect as the four forces had on what the ocean liner. Okay, so let's look at how we are going to do this. We know that the force is going to be the same as the sum of the forces of the four tugboats. Okay, and then since you want it to have the same effect on the hull, then the rotational effect it will have, the rotational effect the single force will have on the hull must be equal to the rotational effect that all the four tugboats had on the hull. Okay, and then in order for us to be able to make the single force have the same rotational effect, you must place it at a particular position, okay, on the hull of the ocean liner, so that it will be able to what's called the same rotational effect. Okay, we can't just put it at anywhere, or we can't just apply that force at any point on the hull and then expect it to have the same rotational effect as the four tugboats did. So you must locate, or you must find a particular point, okay, on the hull where we can apply that force, that single force from the tugboat, okay, in order for it to have the same rotational effect as the four tugboats did. So let's look at how we are going to do this. So what you are trying to do now is that you are trying to say that the rotational effect that the single force will have must be equal to the rotational effect that all the four tugboats will have, right? And then we got that value to be minus 1035.5. So that means that the rotational effect that the single force will have on the hull must be equal to that value. Okay, and then we calculate the couple moment by taking the cross product of the position vector, okay, and then the force. Okay, so in this case, the force will now be our resultant force. Okay, and then that will be equal to minus 1035.5. Okay, that's what you got for the rotational effect. Okay, for the magnitude of the couple moments that the four forces will have on the ocean liner. Okay, so now we know the value of the resultant force, we know the component, okay, but we don't know our position vector r. Okay, but for the position vector r, one of the components will be easy to find. Let's look at that. So looking at the figure here, you will see that the distance, okay, from point O here to the surface of the hull, okay, is 70 feet, okay, which is this distance that we have here. Okay, it's what, 70 feet. So that means that so far as we are applying our force on this surface here, okay, the distance, okay, from the point O to the surface is going to remain what, 70 feet. Okay, the only distance that we can't tell straightforward will be the distance in the x-axis direction, and then that is the distance you have to find now in order to get the complete position vector for the single force. Okay, so if you get that position vector, you'll be able to know where specifically you can apply that single force on the hull in order for the force exerted by the single tugboat to have the same effect as the four tugboats did. So let's look at how we are going to do this. So we know that so far as we are applying the force on the surface of the hull, our distance in the y-axis direction is going to remain 70 feet. Okay, but for the x direction, we don't know where specifically we can put it. Okay, because you can place it anywhere. Okay, it can even be in this direction, but you don't know where specifically. So we will have to find the x value in order for us to get the actual position where you must apply that single force for it to have the same effect as the four tugboats had. So let's look at how you are going to do this. So now our position vector will be xi, okay, plus 70g. That's what we have for now. We don't know what the x is, so you have to find the x. And since the rotational effect that the single force will cause must be equal to the rotational effect that the four tugboats caused, we can use this equation to find the value of what, x. Okay, so you're going to have xi, okay, plus 70j, okay, the cross product of that position vector and then the resultant force, which is 9.04 I minus 9.79j, okay, and then this will be equal to minus 1035.5. Okay, so now let's do the cross product. Okay, so for the cross product, you know how to do it already. You're going to have minus 9.79 multiplying x, okay, and then minus 70, okay, multiplying 9.04, okay, and then this will be equal to minus 1035.5. So let's simplify this and see. So we have minus 9.79x, okay, minus 70 multiplying 9.04, okay, this will give us a value of minus 632.8. This will be equal to minus 1035.5. So let's simplify this. We have minus 9.79x. This will be equal to minus 1035.5 plus 632.8. Okay, let's further simplify this and see. So you're going to have minus 1035.5 plus 632.8. This will give us a value of minus 402.7. So let's divide and see what you are going to get. Okay, so you're going to have x, the negatives will cancel, so you're going to have x to be equal to 402.7, okay, divided by 9.79. Okay, so let's see what you're going to get for x. So 402.7 divided by 9.79, that'll give us a value of 41.13, and then the unit is feet. So what that means is that the single force that the single tugboat will exert, okay, will be the same as the forces that all the four tugboats exerted on the ocean liner, okay. And then for it to cause the same rotational effect on the ocean liner, we must place it at this position. That will be 41.13 in the x-axis direction, okay, and then 70 feet, okay, in the y-axis direction. So if we apply that single force, okay, at this point on the hull of the ocean liner, then that single tugboat is going to have the same effect that the four tugboats had on the ocean liner.